Hello, we are Group 10 and this is our final video of our Fluid Oscillator project. There are three main components. The first one is water pump, which has 70-liter flow rate per minute. The second and the most important one is Fluid Oscillator. On the left you can see the 3D printed version and on the right you can see the final CNC version. Furthermore, the connection components. From left to right you see pipe and clamps, flap, pipe reduction and valve. Finally, you can see the all assembled parts and their names here.
The functionality of our product is about wider cleaning of the windshields of passenger cars, therefore it should have sufficient oscillations. To achieve the oscillations that we based on Hyundai Tucson's rear windshield glass, there are three different manufacturing tools which have been used. There are 3D printer, carpenter and CNC. The 3D printing and the carpenter methods were used to make our initial prototype since they cost relative to the CNC. Considering our elimination of many different designs, we have produced 4 initial prototypes and 1 final prototype. This number is higher than we expected. First prototype is printed in school by using PLA, as you can see in the image, plastic filament. This suffered from working principles of the printer like supports, height, and etc. Furthermore, we fastly delivered the second prototype by changing the design and the filament type also. This became more successful. However, since it is challenging to connect this plastic 3D printed prototype to our pipe, we sought another manufacturing methods and we found out that carpenter could do the job. We have worked closely with the carpenter in his manufacturing processes. We also made a couple of adjustments like placing a plexiglass to observe the fluid movement in the mixing chamber of the fluid oscillator. We have used again 2 different designs to optimize our final prototype in carpenter. We had chance to test them all in our system. One of the 2 actually satisfies the oscillations that we've been seeking for. We conducted many tests on this one and without losing any time. We have made the fastest possible production in CNC milling machine in Sakarya. We obeyed the universally approved Toyota production system aspects like the just-in-time Genji-Genbutsu rules, which tells that the best solution to problem can be found out by using itself in the production line, not from the office. So we have traveled to Sakarya and followed the production in person. The manufacturing took 2-3 days when adding before and post processes of it. We have produced in 2 symmetric parts and welded them together with the male conductor as well. The material used was carbon steel leather and perfectly satisfies our design requirements. When we tested the final prototype at different flow levels, it provided the oscillation that is enough to place it on the SUV's rear windshield like Hyundai Tucson's, which has a dimension of 130 to 45 centimeters. This is the second design of the carpenter manufactured prototypes, and you can see the oscillations from the plexiglass, which is a transparent that you can observe the mixing chamber. This is the final prototype which we produced in the CNC, and you can see the oscillations clearly at higher flow rates.
The previous design that we have used in second meeting was tested in real life with the part that Carpenter has manufactured, and as a reminder, its analyses were shown. By this manufactured model, we observed the fluid's movements both in the mixing chamber and the feedback channels, where the vertices have been observed, which resulted in almost 5 to 10 degrees of oscillations in the outlet. Since we wanted more, we have changed the design according to the most known area that fluid oscillators are used, the aerospace industry. In rockets, they place the fluid oscillators normal to the ground, which is 90 degrees. Therefore, we changed our design such that it is placed 90 degrees to the ground. Also, since the pump that we ordered was not sent and a different pump with a less flow rate than our ordered product was sent, we have done all the analysis according to the new pump. Moreover, the flow rate was too high for the fluid to oscillate, so we made the tunnels rectangular instead of circular to decrease the flow rate by increasing the area, which results in a decrease in the velocity of the fluid. Then we assumed K-omega model to see the vertex at the edges better and no slip conditions on the walls for our new ANSYS model. In this slide you can see the mathematical model that we used to change the flow rate and the velocity of the water by using Bernoulli's equation. However, since we have tab in our design, we can adjust the flow rate manually too. We turned the tab to a certain level and then we measured how many liters of water that the pump pumped in 1 minute. It was approximately 22 liters per minute and we used this flow rate for our fluent analysis. Also, according to our literature research, by changing the outlet angle the oscillation of the fluid can be adjusted, but there is a trade-off with the length of the fluid that is being splashed. Therefore, we change it such that the angle is 60 instead of 30, and the reason why it increases the oscillation is that the fluid tends to move next to the wall while oscillating. In compared to the previous model, it has been observed that the frequency of the oscillation was decreased, therefore the oscillation was easier to track. Also, the angle of oscillation was increased, and the movement of the fluid was clear left and right, such as the example that our supervisor Metin Hoca showed to us, which was done in the Ohio State University in 18 months. Lastly, to check whether the strudel number, which is associated with the oscillation of the fluid, was in the range as we expected, we have used the lift force versus flow time and lift force versus strudel number graphs. We have calculated the frequency by the first graph, which is 0.6 Hz, and since D and U are 8 mm and 18.23 mm per segment, the strudel number was found to be 0.2633, which is the acceptable range for shapes that has curved edges.